Okay, so I'm gonna cruise through the first few questions. I've already done this video before. This is actually my third time through it, and the first two times it's crashed out at the hour 30 mark. Just fantastic, an hour 30 of doing all that stuff. So what I'm going to do is I'm just going to show a quick work through of my homework set, and then I'm going to start where the last video canceled out because yeah, anyway. So first problem, motion's done by this. We have to determine the time, the position, the velocity when a equals to 0. So what we're going to do here is we're going to take the first derivative of that. It's going to be our velocity. Second derivative of that is going to be our acceleration. We set our acceleration equal to 0, and then that's going to give us our time in seconds. After that point, what we do is we take this time in seconds, we plug it into our position, and we plug it into our velocity. And that gives our total final displacement. I guess you could say a velocity or position. So velocity, again, that's the derivative of this function here. Acceleration, derivative, again, of this function. And then we set a equal to 0. Once we have a equal to 0, we can solve for this. Divide it by 12, gives us this here, separate it out, 3t minus 2. And then we can set that equal to t equals 2/3, and t equals 1/2. Negative 1/2 is not a valid time value, so we know that. So we know we need the 2/3 at a equals 0. At that point, we use that, we plug it into the velocity and solve. That's going to give us negative 8.56 meters per second. We then take that same 2/3, plug it into our time function, and that is going to give us 0.259 meters. Okay. Projectile enters a resting medium at x equals 0, at position, x equals 0, with a v sub naught of 900 feet per second and travels 4 inches before coming to a rest. Assume velocity is defined by v equals v sub naught minus kx. So first what we need to do is figure out what that constant is, because it's essentially functioning as a spring. So we need to figure out the acceleration of the projectile, the initial acceleration, and the time required for it to penetrate 3.9 inches into the medium. So what we're going to do is we know that our final velocity is going to be 0. And we know that our initial velocity is given by 900 feet per second. So what we do is we're going to set that to 0 is equal to 900 feet per second, and that's going to equal negative k, and that's going to be a third for x. The reason that's a third is because we know it travels 4 inches before it comes to a rest. 4 inches divided by 4 inches in a foot is a third of a foot, so that's going to be a third there. So k of a third is equal to essentially 900, because the negatives cancel out, and that gives us a k value of 2700. So that's our k, our spring constant, so to speak. Now, we know that the change dv dt, if we go across and we take the derivative of everything with respect to time, we are going to have dv dt is equal to dv dt equal to dx dt. Now we know that dx dt is v, right? So derivative with respect to position is velocity. So dv dt is acceleration. Dv sub 0 at dt is the initial acceleration, which is going to be 0. And then we know that dx dt is going to be velocity. So what we do is we're going to set that equal to a is equal to negative k times velocity. And velocity, in this case, is going to be the initial velocity. So a is equal to negative 2700 times 900 feet per second, which gives us a initial velocity, initial acceleration, of negative 2.43 feet per second squared. So now we need the time required to penetrate 3.9 inches in the medium. What we're going to do here is we are going to take this function and we're going to integrate it. And the reason we integrate it is because we're actually trying to find everything with respect to time. So if we integrate velocity and integrate position with respect to time, then we are able to solve for t. Now, the way we do that, it's going to be a little bit tricky. We know that dx dt is equal to v, so we just sub that in. So then we can multiply the v sub naught minus kx over, and v sub naught kx. We can move over. Hold on one second. I'm just trying to make sure my phone's not dying. I'm back. Over and then move the t over. So we're going to have dx is equal to v sub naught minus kx dt. I screwed that up. Sorry. So we're going to have dx dt times that by dt, and then divide dx by that term because we want to isolate the x term. So we're going to have dx v sub naught minus kx equals dt. At this point, we can do integration by substitution. So we're going to set u equal to that, so we can just do a derivative of u, and then we're going to need to solve for dx. So u equals to v sub naught minus kx, and then du is going to be, knock out the vo, is going to be negative k dx, because the derivative of x is dx. That's going to solve for du over minus k is equal to dx. So we go here on our integral, and we're going to have 1 over u is equal to du minus k. We can separate out the k, that's what we did here. And then we take the indefinite integral. It's definite, but the integral there is equal to the integral from 0 to t of dt. That gives us the t. So what that's going to do is it's going to give us negative 1 over k, ln of u is equal to t. Subbing that our function back in, we're going to have t equals negative 1 over k, ln the natural log of v0 minus k. At this point, we can sub in our values. And now we have to remember that this is going to give us our value from x to 0. So we're going to go through, and that is going to give our first up 900 minus 2700x, and our second term here is going to go to 0 at the end because x is equal to 0. From there, we will continue to where our t, I put on here negative 1 over 2700. But we can figure it out. So let's see, 3.9 divided by 12. 0.325. .00136 is what the answer comes out to. Yeah, which the answer is 1.366. So we got that right. Okay. So, question 3. Question 3, ball strikes surface of the lake with a speed of 16.5 feet per second. Ball experiences an acceleration of 10 minus 0.8 v in feet per second and feet per second squared for acceleration, respectively. The ball takes 3 seconds to reach the bottom of the lake. So we have to figure out the depth of the lake and the speed of the ball when it hits the bottom. So, what we know is A is dv dt. Change of velocity or change of time. So we set that equal to 10 minus 0.8. That way all our terms are in v and t. And then we do the same thing. We're going to times by t on both sides and divide by 10 minus 0.8. That gives us this term right here. We are then going to do an integration of v0 to v final, dv 10 minus 0.8 v, and go from 0 to t for the integration on dt. That's going to give us this term, negative 1 over 0.8, natural log 10 minus 0.8 b final minus natural log of 10 minus 0.8 b initial is equal to the time. We then multiply both sides by 0.8. At this point is really just algebra. Raise it to the negative, raise everything to by e to cancel out the natural logs. And then times that by the bottom term here, the denominator on the other side. So we're going to have 10 minus 0.8 b final is equal to e to the negative 0.8 t, 10 minus 0.8 b initial. And then subtract 10 over here, divide by 0.8 from the b final, and then at that point, b final is left on its own on the one side, and we can sub in the 3 seconds. So it takes 3 seconds to reach to the bottom, so we could find the speed of the ball when it hits the bottom. So that's going to be 12.86 feet per second. Right there. Now, we know that v final equals this term. What we can then do is keep going through with that term and just solve for that and integrate it. When we integrate it from velocity, it's going to give us our position function. So once we have position, we can put in the 3 seconds, and that will give us the depth of the lake. That's how far it traveled in 3 seconds. We know that 3 seconds gets to the bottom of the lake. That'll give us the length, or the depth of the lake. So we work through till we have negative 3.2 e to the minus 0.8 minus 10 minus 0.8, and dividing both of these terms by 0.8, we're left with negative 4 e to the minus 0.8 minus 12.5. Now, again, the integral, take the integral of both sides, knowing that the velocity is dx dt. So dx on here, and then we multiply this other side by dt. And then we integrate with respect to x, 0 to x, and integrate with 0 to t. So what that's going to do is going to give us this term, x is equal to 12.5x plus 4. Plus 4 minus 1 over negative 0.8, e to the minus 0.8, and then we're going to go from t to 0. So what we do is we can separate out those terms. We know that e to the 0 is going to be 1, so we can then do a little bit of trickery here and go negative 5 over e to the minus 0.8, and negative 5 because negative 0.08. 4 divided by that term gives it 5. And then negative 1 term right here, and then do a little bit of cleanup, type in 3 at the x term, and that will give us this here, and x is going to go to 42.5 minus 0.45, which gives us 42.05 feet as far as the depth of the lake. Now, the fourth problem is we have a jogger. Based on the observation, the jogger speed can be approximated by this term right here. We can determine the distance when t is equal to 1 hour, the jogger's acceleration in feet per second squared, and the time required for the jogger to run 6 miles. Now, again, as before, we know that the velocity is the change in position with the change in time, dx dt. So what we can do is we take this function here, and we equal it to dx dt, and then same thing as before, as we separate our x's and then our t's, and we integrate. So that's what we did here, is multiply both sides by dt, and then divide dx by this term here. We then integrate from 0 to x, and integrate from 0 to t. This one we will have to do integration by substitution. We have to do set u equal to this term here, and the derivative, this term here, which when all said and done, we're going from 0 to u, from du negative 0.04 u to 0.3, and what that does is we can pull out the 1 over negative 0.04 and keep the u to the minus 0.3 because it's on the denominator. At this point, we know that we can integrate it, and it gives us u to 0.7. 0.7 minus 1 is negative 0.3, so that's why if we take the derivative of this, it'll give us this term up here. So we're on the right track. At this point, we can then subtract times 0.04 by 0.07 and have 1 divided by that number, and so that gives us our negative 35.7. At this point, we are still have to do it with respect to our x's, sub in our x's. So we sub back in our x's equal to 7.5t, and then separate out from x to 0. So it leaves us with this term here and a 1 term minus a 1 term. Divide both sides by 35.7, gives us 0.210 on this side. And then here we can just move our 1 over here, shift it over. And then if we take the root of 0.7, so not the square root or the cube root, but the 0.7 root, that is essentially saying we're going to divide the 1 here by 0.7, right? So that's what we're doing here at this point. We're going to take the root of 0.7 here, and that means on this side we have to divide by 1, or divide the 1 over by 0.7. And then what that does is we can then isolate x, and then type in our t, or for the initial, the distance at 1 hour. So we solve, and that gives us 7.147 miles. Now, this part's a little bit trickier. At this point, we're trying to figure out b. B is going to be the jogger's acceleration in feet per second squared at t equals 0. So we need to integrate our velocity function. Now, we know here that the acceleration is the change in velocity with respect to time. But we also know that velocity is the change in x with respect to time. So we can actually sub in for our dt term, and what it'll do is acceleration will end up being velocity with respect to the change in velocity over the change in position. So what we then do is we got to sub in those terms for that. So d of the change in velocity with respect to position, and then we multiply that through, so it's going to be d dx is equal to 7.5. We pull out the constant, and then d dx of this term right here. What we then do is, excuse me, what we then do is we have dv dx on this side, and we will times, that's dv dx, so we get acceleration, we have to actually multiply our velocity times this term. So that's why we have this huge long term right here. At this point, we can pull out our 7.5 squareds, and then we have this term right here, 0.3 negative 0.4, and then 0.3 minus 0.7. So that gives us a minus 0.4 as far as what we're raising it to the power 2. At t equals 0, the x is 0, so we know that we're solving for t0. So we sub in our x 0 here at this term, or sorry, at this term. So that's just going to remain a 1 to raise to the negative 0.4 power down here. That gives us a negative 0.675 miles per hour squared. Now, to get to seconds squared on that in feet per second squared, we know there's 5,280 feet for 1 mile, and we know there's 3,600 seconds per an hour. We have an hour squared, we want seconds squared. That gives us negative 2.75 times 10 to the minus 4 feet per second squared. Now, for C, what we're doing is we're doing the time required for the jogger to run 6 miles. So we're going to use this part of our function here, where it's equal to t, and we have both position and time. And what we do is we're going to put in 6 for our position, and then we're going to shift over this minus 1 over here and divide by negative 0.1. That can solve for our t. We do that, and then t goes to 0.8 hours. That's about 49 minutes, which makes sense. It takes 49 minutes to run 6 miles. It takes 1 hour. The jog can run 7 miles. So that's about right. It's within that limit. So question number 5 is asking about the acceleration due to gravity of a particle falling to the Earth. We need to calculate the escape velocity for a radius equaling 3960 miles. So essentially, if a particle is on the surface of the Earth, that's a radius of 3960. The radius of the Earth is 3960. What's the escape velocity? So the escape velocity of a particle on the ground. So we know that acceleration, again, is the velocity with dv dx, or in this case, dr. So the change of velocity with respect to position. So what we do is we can actually multiply both sides by dr. So we're going to have a dr, acceleration with respect to radius, and velocity with respect to the change of velocity. And then what we do is we can integrate those. And what we'll integrate those is, we know that the hint we were given is that as r, the radius, approaches infinity, the velocity is 0, which makes sense. You know, the further away you are from Earth, the escape velocity is 0. So what we do is we're going to integrate, and those are going to be our limits. Is we're going to integrate, we use our acceleration function of negative g, big R squared over little r squared. So we're going to have that here, and we're going to be integrating from 0 to infinity. And again, as you go to infinity, your velocity approaches 0. So on the other side, we're going to be integrating velocity, and it's going to be going from our velocity term on the ground, and that is going to go, as the further we get away from Earth, it's going to go to 0. So we can integrate both sides. What we do is we have our negative gravity term times 3960, the big R squared, going from 0 to infinity of 1 over r2. That's also saying r, essentially saying r raised to the minus 2. So we move on from that, and that's going to be 1 over r is the integration for that, right? Or r minus 1. So that's going to give us this term here. Solving through, placing in infinity for r, that's going to be pretty much, that's going to be 0. 1 divided by infinity is essentially 1 divided by a gigantically large number, which is going to be 0. So we can just go away with that term, and we can keep this positive 1 over r term. Now, 1 over r is essentially going to be the radius that we're away from Earth. Multiply both sides by negative 2, gives us 2g times 3960, the radius of the Earth, and we are at the radius of the Earth. We're at the surface of the Earth. That's what our little r is here, and that gives us our v squared. We're going to put in 32.2 feet per second squared for our gravity, and we are going to square root and solve for velocity. We're going to do some manipulations here, times it all by 5280, so we can get the miles out of the way and we get feet. That gives us an escape velocity is 36,695 feet, or 3.6, round it to 7 times 10 to the 4th feet per second. There. All right, question number 6. Athlete pulls a handle to the left with a constant acceleration. We know that after B has been lifted 4 inches, its velocity is 2 feet per second. We determine its acceleration of A and B, and we determine the velocity and change in position of the handle A after 0.5 seconds. So the way we can do this is a graph of what's going on. Now, as A, we have a motion in the negative x direction, and we have motion in the positive y direction. And if you look at the graph, it's at about a ratio of about 3.1. So what you can do is you can actually set A for every distance, as far as it's... I think this is wrong. This is actually, I made a mistake here. It should be 380 to the x plus b to the y. Because for the distance, oh no, that's right, sorry. So for the displacement of x, you have to have 3 displacements of y to match. So that's going to be about right. Or another way of saying it is, another way of saying that would be, for every 1/3 of the motion in x, you're going to have 1 movement in y, or 1 displacement in y, which is about right. So we know the acceleration is constant. That's one thing that's mentioned. That means we can use the kinematics equations. So what we're trying to do is we're trying to find a displacement. So we're going to use our displacement term, which is going to be v squared final is equal to v squared initial plus 2 times acceleration times displacement. The displacement in this term is going to be in the y direction, and we know that the 4 inches that are being displaced in the y direction is 1/3 of a foot. So what we do is we know that we're given the initial velocity as 2 feet per second. So we're going to set that to 2 feet per second. 0 for the initial velocity, because it's at 0, it's at rest, and 2, and then a third here for the displacement, 1/3 of a foot. Solving through, that's going to give us in 4 feet squared over second squared is equal to 2/3 feet per second. 3 times 4 is 12, divided by 2 is going to be 6. So that's going to give us a acceleration in the y direction at 6 feet per second. Now what we can do is we use that and we plug it into our equation up here, or this equation here, right? And so that's going to give us our x displacement. Another way to think about it is that is essentially going to be the distance displayed in the x direction is going to be 3 times as large as the distance displayed in the y direction, because the distance is 3 times greater. If you're traveling 3 times greater at the same time, you have to be going 3 times faster. So what we're going to do is we could easily just take that and multiply it by 3, or we could put it into our equation, which is going to just give us that same thing multiplied by 3. So ax is going to be equal to negative 18 feet per second squared, which is pretty intuitive, right? Our acceleration is going to go this way. So it's going to be in the negative x direction. Now for the velocity term, we could just use, again, kinematics equation on this one, because so v final is equal to v initial plus acceleration times time. We know it's going to be going for 0.5 seconds for v, so we need to figure out the velocity and the change in position of the handle a. So v final is going to be equal to 0, is for v initial. We know it's going negative 18 feet per second squared in the x direction. For half a second. So that gives us a v final of negative 9 feet per second. The change in position, again, we can do it in kinematics. So it's going to be our final x position is equal to our initial plus our velocity function as v of t, and 1/2 of our acceleration times t squared. So we move that over and we have a delta t term. V is initially 0, and then we can just type in negative 18 feet per second for half a second. And that's going to give us a delta x of negative 9 times or quarter. So that gives us a total of a delta x of 2.25 feet. So now we're looking at a parachutist problem. The parachutist is falling at a rate of 200 kilometers per hour, opens at 600 meters. There's constant deceleration. The constant deceleration at 50 kilometers per hour from 586 meters height to 30 meters. Then he turns down the wind for a further slow descent. What we have to do is we have to figure out the time required to land after obeying, and B is what the initial deceleration is. So what this does is giving us 3 time intervals. There's one from when he opens the parachute, or she, at 600, and goes from there to 50 kilometers per hour. From the initial 200, and that is going to be from 600 meters to 586 meters, so that's 14 meters. So the way we do that is we can convert that to meters per second. 200 kilometers per hour is 55.55 meters per second. 50 kilometers, 13.9 meters per second. We subtract the difference, divide by 2, and that gets us our average, or for that time period. That's going to us 34.72 meters per second. So what we then do is we know that the distance covered in height is 600 meters to 586 meters. That's 14 meters, and we divide that by the change in velocity. So that gives us a 0.403 seconds for the first time interval. The second time interval is going to be the 586 meters in height to the 30 meters in height. And that's going to be a constant 50 kilometers per hour, or the 13.8 meters per second. So what we do is we take the 586 minus 30, because that's the actual distance traveled, and we divide that by 13.89, and that's the constant deceleration through that time period. So what that does is it gives us 40.0 seconds for that second time interval. The third time interval is when the parachute is going 13.89 meters per second down to 0. We divide it by 2, and that gives us an average velocity change of 6.945. And now we know that it's 6.945 meters per second over 30 meters. So if we divide that through, that's going to give us a 4.32 second time change for interval 3. Now we know the time interval total is going to be time interval for time, the first, second, and the third interval. So t total is equal to t1 plus t2 plus t3. So we have our 0.403 plus our 40.03. plus our 4.32, and that gives us a 44.753 second total time interval. The initial deceleration, if we assume a constant deceleration, we can use using kinematics. We know that the delta V is equal to AT, or V equals V naught plus AT. What we do is we move the V naught over, and we know that another way to think about it is like V final minus V initial. V final at this point is 13.89. V initial is going to be 55.55. So, or another way to think about it, 200 kilometers per hour is V initial. V final is 50 kilometers per hour. That's for the initial time period of deceleration. And we know that that's going to happen over 0.403 seconds, our first time interval. So we do that, and that gives the deceleration of negative 103.4 meters per second. Okay, I think what we can do, I think we can stop that right there and call that homework 1. Or actually, I'll do the next one, and then I'll call this the part 1 for homework 1. And I'm just going to go over this pretty briefly. It's a pretty big, hefty problem, but it's really not hard. It's giving us a 3D motion of a particle given by a position vector, and then it wants the magnitude of velocity and acceleration. It's pretty much just plug and chug and mind your negatives. We know that a position vector, is given by your I, your j, and your k functions, or your x, your y, and your z functions of vector. So it's going to have an I term, a j term, and a k term. The derivative of the position is going to be your velocity. The derivative of velocity is going to be your acceleration. So the main problem here was really minding the product rule when taking the differential, and that was really it. It makes it kind of hefty on the plug and chug, but that's really all it is. And we know that the magnitude is essentially everything squared, the root of everything squared. So for a velocity, the velocity squared is equal to the component in the x direction squared, the component in the y direction squared, and the component in the z direction squared, and then you take the root of that. So I'm not going to go through all this. It's pretty simple. It's like, right, the derivative of cosine is negative sine, blah, blah. The derivative of sine is cosine. So when we take the derivative of this position function, it gave us this velocity function. Take the derivative of that with respect to time, it gives us our acceleration here. And then do the magnitude, we multiply our components together, which after all this fun work, minding your omegas, it gives us this answer right here. Velocity is equal to the square root of r squared 1 plus t squared omega squared plus c squared. So, cool. That was fun. Now, we need the magnitude of the acceleration, which again, the magnitude of the acceleration is exactly like the magnitude of the velocity. You take your x component, your y component, your z component, you square them, and then you take the the square root of that. So that's me doing this here, which gives us the final acceleration of square root of r squared over 4 omega squared plus omega to the 4th t squared. Okay. Then I think I have about 3 problems left, so I think I'm probably going to stop that. And we'll do that. Check that up tomorrow. Thanks for watching.